Welcome everyone to the Celsius lecture. It is an honor for me to moderate this first session that will focus on science in the field of climate change. It is an honor to introduce the Celsius lecturer for this year, Professor Sonia Seneviratne. Professor Sonia Seneviratne is a leader in the field of climate change. She is a professor for land and climate dynamics at the ETH Zurich. She has been the lead author of many IPCC reports, including the special report on extreme events. She has many awards and international prizes, including the Musselwhite Medal from the American Geophysical Union, and she is currently running a ERC Consolidator grant by the European Research Council. Without further introduction, I would like to give the floor to Professor Sonia Seneviratne. She will give the lecture entitled Droughts and Heat Waves in a Changing Climate, Why Every Year Matters.
Well, thanks very much for the kind introduction and the invitation to speak at this Celsius lecture. It's a great honor for me, and I should say I would have been really happy to come in person to Uppsala, because when I was a student, I considered to do an exchange of 1 year at Uppsala. In the end, I went to Zurich, and I ended up in Zurich, but it could have been an option for me to go and study in Uppsala. So I will speak about extremes in a changing climate and why every year matters. I changed slightly the title also to include other extremes beyond droughts and heat waves. So most of my presentation will focus on the last IPCC reports, on the IPCC ER6 Working Group 1 report, which was published last August. I was coordinating Chapter 11 on climate extremes, and I will also show a few results from our research group. So I want to start with this picture, which shows our planet Earth. This is our home, that's where we are living, and obviously we don't have any other planet, so we should be making sure that we can still live here in good conditions. I think what is also very impressive is if you look at this picture of the atmosphere, you realize that all of the weather and climate is happening in this very small piece of this small layer that is enveloping our planet. And obviously, it's not a lot of space, and if we modify it, then it can have strong implications. So I wanted to start with reference to Anders Celsius, and obviously he's playing a very important role in climate science because thermometers are at the basis of our measurements of temperature, and that's from this that we know we have a global warming. So Celsius plays an important role in modern climate science. Without him, we wouldn't have the iconic 1.5 degree limit of the Paris Agreement. I think you have all heard about this. So basically, in the Paris Agreement, the aim was set to limit global warming well below 2 degrees and if possible to 1.5 degrees, and it's 1.5 degrees Celsius. So that's a really important aspect. About temperatures, so as mentioned, temperature measurements are at the basis of the main measure that we have of climate change, which is global warming. We have measurements of temperature all over the globe, as you can see here, and those measurements reveal that we have had already 1.1 degree of global warming in the last decade, so in 2011 to 2020. And so you can see this as a similar measurement as you would have to measure the health, for instance, of a child. We have the way to measure what is the state of the climate system in different locations, and this is telling us that something is not okay. We are outside of balance. So I'll say a few words about the greenhouse effect. So the greenhouse effect is that we have different greenhouse gases which trap long wave radiation, and of course if we emit more of them, then we have even more heat that is kept. Without the greenhouse effect, the mean global temperature would be about 33 degrees lower. So basically we have some natural greenhouse effect, which is good, but the influence of the human emissions on the Earth system means that we have an additional greenhouse effect that is due to human activity. As mentioned, this is leading to 1.1 degree of global warming in the last decade. Now you could say maybe that doesn't look like a lot, 1 degree compared to a total effect of 33 degrees, but if you think of the temperature of the human body, 1 degree of fever or more than 1 degree of fever already indicates that you have an illness. And so it's also already a sign of concern. I wanted to mention some basics of the climate science. It's really a well-established science. So the basics are established since a very long time. Here, mentioning as first, actually, a Swedish researchers, Svante Arrhenius, who received the Nobel Prize of Chemistry in 1903. And so it was at the basis of the science that shows that greenhouse effect due to CO2 concentration is substantial. It was already estimated more than 100 years ago. So the basis of the climate science is well established since a very long time. So I wanted to mention other recent Nobel Prize winners, which were just awarded the Nobel Prize last year, which is also showing that more recent development of climate science are also extremely well established. So Suki Manabe and Klaus Hasselmann received each quarter of the Nobel Prize in physics. And they were working on the one hand on climate modeling and also on the attribution of observed signal in the climate system, two very important fields. And you see that these two essential elements of climate science have been now recognized as being very well established. So as mentioned, I will speak mostly about the last IPCC report in which I was involved. So it's basically a report that is prepared by the Intergovernmental Panel on Climate Change under the UN. There are very large reports that are prepared about every 6 to 8 years. And I've included here also some pictures of the team that was working on this report. So we had a very large team of people. We had about 234 persons who were authors on the report. And of course, when we started working on it in 2018, we could meet in person. And at the end, we have to finish everything online. I was coordinating chapter 11 of that report together with Subin Zhang, a colleague from Canada. And so we were working in this chapter on climate extremes, and I will mostly focus on the conclusions of that chapter. I should say that was a great team to work with, and we had contributors from all over the world. So when we were working mostly virtually, this meant that always somebody from us had to be up in the middle of the night. So I'll come back to this measure of global warming. Basically, what is the mean global temperature change? I already mentioned we had 1.1 degree of global warming in the last decade. The evolution of temperature is shown here in the left. And what you see very clearly is that the evolution in the last about 150 or 170 years is really extraordinary. So you see this very strong increase in this very recent period. So the current temperature level is unprecedented in more than 100,000 years. I think that's an essential point. So the temperatures that we have at the moment, based also on paleo reconstruction, shows that basically we have never had this type of temperature in the past. For instance, during the development of human civilization, when we had the first people who were starting to do writing in about 5,000 years ago. So an agriculture developed under temperatures that were lower than today. And I think to me, this shows how dramatic the situation is. We are truly having temperatures that are without precedent in a long time in human history. The largest part of this warming is irreversible for several generations. That's a really important part because once we emit CO2, CO2 stays very long in the atmosphere. It stays 700 to several thousands of years. This means that the level of temperature warming that we have reached will stay this way for a very long time. And so that's different from some other problems. For instance, in the past, we had issue with ozone hole, but the pollutants that were leading to ozone hole had a rather short life in the atmosphere, which meant that once we stopped emitting them, their concentration could decrease fairly quickly. This is not the case in the case of CO2. Regarding our contribution to this warming, is very clear. So that the conclusion of the IPCC ER6 report is that it is unequivocal that human influences warm the atmosphere, ocean, and land. And the best estimate that we have of our contribution is about all of the warming is due to human emissions. That's what I'm showing on the left here. In black, you see the evolution of observed temperature. And in brown, you have simulation, which includes both human and natural factors. So for human factors, it's mostly CO2 emissions, land use change. And then in blue-green here, you see the evolution where you don't have the human factors, you only have natural factors. And it's very clear that you can only get the warming that has been observed if you include the human factors. And what we find is the total magnitude of this contribution is about the level of warming that has been reached. So about all of the warming observed is due to human influence. Another figure that I often show, because to me, it summarizes very well the situation we are in, is this figure, which shows the CO2 concentration in the atmosphere at Mauna Loa, that's in Hawaii, but it's a good measure of the average CO2 concentration in the atmosphere. And what you see is that the CO2 concentration is keeping on increasing year after year. The last record was in May last year, and we expect that this year it will be again a new record. So you see that the CO2 concentration keeps on increasing, and there is really no change in sight. So, for instance, when you consider that the first IPCC report was written in 1990, that's when there was the first realization that probably we have a global problem and we need to act. There was also the Kyoto Protocol 2005. There was the IPCC Nobel Peace Prize. So IPCC received the Nobel Peace Prize 2007. The Paris Agreement, which decided to limit global warming well below 2 degrees, if possible to 1.5 degrees. There was an IPCC special report on 1.5 degrees. Of course, a very important global scale, and also in Sweden, a movement started by Greta Thunberg about 2018. And the COVID crisis, where we had actually less CO2 emissions. If you think of all those events where we had the realization that we have a problem, we need to act, actually you don't see this in this curve. You just see increasing CO2 concentration year after year. And so this shows that we really need to have a change in our society, as we won't be managing to change the course. And the course means having normal CO2 emissions, which would mean a stabilization of CO2 concentration. Now, what are the sources of CO2 emissions? And this is something we know very well. It's well established. Basically, it's mostly burning of fossil fuels. And I think we just need to realize if we want to stop emitting CO2, what we need is to stop burning coal, oil, or gas. With this, we would already stop most of the emissions that we are having at the moment. So obviously, any change in our everyday life will lead to less burning of CO2, for instance, not having a petrol car and not basically using any form of fossil fuels, we make sure that much of our CO2 emissions are disappearing. Now, the rest of the emission is due to land use change. And of course, in some countries, like Brazil, is very important where you have a lot of deforestation. That's also another threat. But you see, basically between land use change and burning of fossil fuels, most of the emissions are covered. And that's where is a solution. We need just to avoid all the sources of emissions. About the link between CO2 and global warming, this is also extremely well established already since the last IPCC report, the one before, which was from 2013, where you see that here you have on the x-axis the cumulative CO2 emissions since 1850. So you look at the total accumulated CO2 in the atmosphere. As I said, CO2 stays very long. That's why it's the accumulated CO2 that matters, because you keep on putting more CO2 in the air. And this cumulated CO2 emissions is directly related with global warming. It's almost a linear relationship. You see in this figure here the observed warming. And of course, there are small fluctuations from year to year, but there is this clear, more or less, linear relationship. And it's the same going forward. So we are more or less here. And basically, going forward, how much warming will reach will depend on how much CO2 we additionally put in the atmosphere. And if we want to limit global warming to approximately 1.5 degrees, then we should follow this scenario here in light blue. And we see this means that actually we have a very limited remaining CO2 budget. Now I'll say a few more words about overall observed change in climate, also in terms of the distribution of temperature changes. If you look on the left, I'm showing here two maps. That's a change in temperature from 1900 to 1980. And then from 1981 to present, and that's a trend in temperature in degree per decade. What we see right away is that not only we have an increase in temperature, but actually there is an acceleration of warming. So the warming since 1981 has been much stronger than the warming before. It includes also Sweden. You see here very strong warming. And so that's an additional issue that we have more warming since about 1980. because we have more emissions, but also because counteracting effects from aerosols have disappeared. So both effects are important, but obviously this problem has become a much bigger problem since about 40 years. In terms of the regional distribution of warming, an important point is the figure I mentioned before, the 1.1 degree of global warming. That's a mean average value. But we have actually more warming on land than in the ocean. One reason is that in the ocean, you can have a lot of evaporation, which takes up a very large amount of energy, while on land, you have more limited moisture. And for this reason, if you compare the evolution of temperature on land and ocean, you have much more warming on land. And so the land regions have been warming on average by about 1.6 degrees. And I should say that actually regions in the high latitudes are warming even more, because there is also feedback with snow. In the regions where snow is decreasing, you have then less reflection of radiation, so you have more radiation being absorbed. So that's an additional factor leading to more warming. So I wanted to mention effects on the water cycle, and that's a bit paradoxical effect, which is on the same time, you have an increase in heavy precipitation in most regions and also droughts in some regions. And this is related to the fact that when you have higher temperature in the air can take up more moisture. So on the one hand, when you reach saturation, which is what you need once you have precipitation, the air will have in total more water available, which means that the total precipitation will be more intense. On the other hand, because the air can take up more moisture, it can also dry up the soils. And this leads to more drying in some regions. So when it rains, we have often the phrase that when it rains, it pours. So we have basically really large amount of water that are falling down when you have heavy precipitation. But you also have more potential for drying soil. And I think this is well illustrated from observation here, which shows on the left the trends in specific humidity. That's how much water you have in the air. And you see clearly that the total water content is decreasing in most locations, also over land. So it means you have more water in total in the air. But the relative humidity, which is computing how far we are from saturation, is actually basically decreasing. It means that you have basically you are having drier and drier atmosphere because you are further from saturation. So at the same time, you have this tendency to moistening in terms of absolute moisture, but drying in terms of relative moisture content. So now I'll discuss a few aspects regarding observed changes in extremes. In our chapter, we looked at a range of different climate extremes, temperature extremes, heavy precipitation, flood, droughts, storms, and compound events. By compound events, we mean several events of different type happening in the same locations. For instance, droughts and heat waves, I mentioned this, but also other type of events, also when you have concurrent extremes at different locations. One very clear conclusion of the report is that human-induced climate change is already affecting many weather and climate extremes in every region across the globe. And I think that's an important message, that we don't have any region that is spared from those changes in climate extremes. There are in every region some change in climate extremes happening. Now I include here some examples of recent extreme events of which we know that the probability was increased. So for instance, in Sweden and also in many other regions across the world in 2018, we had a heat wave, and which was also associated with strong fires. And this very strong heat wave in many different locations. There is studies showing that it would not have been likely to happen without human-induced climate change. Then we had some other events also associated with fires, so this kind of combined effects of heat waves and drought. So for instance, in Australia, 2019, 2020, I think we have all seen those pictures, which were dramatic. And actually, this event led to a very strong release of CO2. I'll mention this afterwards, because of the burning of forests, most CO2 was emitted to the air. It was corresponding to about 2/3 of the CO2 emissions of the country. So it's also a strong contribution to climate change. In Siberia, there was again a very hot temperatures, also associated with fire. This was 2020, for the first time, a temperature of 18 degrees was reached beyond the Arctic Circle. And then in 2021, we had a whole range of events that could have filled even more space with all those events. One example is a very strong heat wave that happened in Canada with temperatures of 49 degrees, 0.5. That's at latitudes that are similar to those in Sweden. So it's obviously very dramatic, and actually one city was burned down in one day. But we also had heavy precipitation. So I also mentioned this, that in many locations we have risk of increasing heavy precipitation. And this year we saw this in Central Europe with many people who died from increased heavy precipitation. And in the Mediterranean region, there was very strong fires and also droughts. So here is a summary of the observed changes in climate extremes. And as I said, the main message is that every region is affected in some way by changes in climate extremes. So the hexagon shows different regions of the world. We have here at the top hot extremes, and you see here Northern Europe. So you see most regions are affected by increase in hot extremes. We have also strong increase in heavy rainfall in many locations, and in some regions increase in droughts, and I'll say a bit more about this. So about the change in hot extremes, it is virtually certain that hot extremes have become more frequent and more intense across most land regions, and there is high confidence that human-induced climate change is the main driver for this change. Another point that was also clear from the literature is that we are starting to see events that are truly unprecedented, where we can say these extremes are so intense, so extreme, that they cannot be explained without the contribution of human-induced climate change. This was, for instance, the case with the event in Canada, where the anomaly was so large, it's almost impossible to explain this without the human contribution to the climate system, to the changing climate system. In terms of heavy precipitation, I also wanted to highlight this because in Northern Europe, you have a particularly strong signal. So the observations show a very strong, clear increase in heavy precipitation in this region and a few others, which means, of course, more risk of floodings because you have more rainfall happening in those intense rainfall days. Here I also include a little bit more details showing in which regions, which stations are showing positive trends in heavy precipitation or negative trends. And you see, for instance, here that you have a very clear signal in Scandinavia, where there is strong increase in heavy precipitation. I'll say also a few words about droughts, and this is actually a topic that was addressed in much more detail in the latest report from IPCC. What we have done also is to look at different types of droughts. So we assess in the report 3 different types of droughts. On the one hand, meteorological drought, that's only lack of precipitation, hydrological drought, which is lack of stream flow, and agricultural and ecological drought, that's when you have a decrease in water available in the soils, for instance, in the form of soil moisture. And this is particularly important for instance, ecosystem, for agriculture. The important point is that those droughts don't change all in the same way, because for soil moisture, what matters in addition to lack of rain is also if you have a change in evapotranspiration, and I mentioned this. So as I mentioned before, if you have higher temperatures, the air can take up more moisture, which means that you have a more tendency for drying of the soil. So you can have a stronger signal in agricultural and ecological droughts compared to meteorological droughts. I'm showing here is a map of observed change in droughts. You see many locations show an increase in droughts. In Northern Europe, the signal is not so clear. I mentioned this afterwards, that actually on average, it's not so clear, but on seasonal scales, there can be some signal, and I mentioned this. The regions that are particularly strongly affected include the Mediterranean and North America. And I think one thing we should be aware is that the regions which are affected are also from the regions which are producing food in many locations. And this is also a concern, of course, for regions not directly affected who might be importing foods from those regions. I mentioned this afterwards. I wanted to show some more results which are from our research group, in which we try to assess what are the historical changes in the availability of water on land. So we looked at the trends in P minus E, so precipitation minus evaporation, in 2 sets of data sets. One was range of land surface models, another one is statistical reconstruction. And the signals are noisy, but on average, we see a dominant fraction of the land areas that shows a drying in the dry season. So that's a change in precipitation minus evapotranspiration in dry season. And the signals are different, but we see overall a tendency towards drying in many locations. Now, if we look at the contribution of changes in precipitation here on the left, contribution of change in evapotranspiration, what is clear is this change in drying or water availability in the dry season is not so much affected by precipitation, but rather by evapotranspiration. So we see a clear tendency to more evapotranspiration, actually even in Scandinavia. It's very small here, but you have also this tendency to have more evapotranspiration, so more loss of moisture from the soils. In additional analysis, we looked at to which extent this change can be attributed to human-induced climate change. And if you look at the correlation of the overall patterns, on the one hand, with simulations that don't include human-induced climate change and simulations that do include it, we find that there is a strong correlation in the case where we include human forcing on climate change, and this cannot be explained by chance. So this means that this overall tendency towards drying on land areas in the dry season can be attributed to human-induced climate change. Now I wanted to say a few words about observed change in compound extremes. I mentioned before, compound extremes are when you have different type of extreme events happening in the same location or even in different location at the same time. And the assessment of the report on this topic is that human influence has likely increased the chance of compound extreme events since the 1950s. For instance, concurrent heat waves and droughts on global scale with high confidence. Also fire weather in some regions of all inhabited continents with medium confidence, and also compound flooding in some locations. What we mean by compound flooding is that regions that are affected by heavy precipitation can have both a signal in heavy precipitation, but then also increase in sea level, which together lead to even more risk of coastal flooding. Another point was that recent literature is showing that the overall area affected by climate extremes is increasing. This means that we have also more risk of having concurrent extremes in different locations. Here I'm showing this as the example of a study from Marta Vogel in our group, which looked at 2018 heat waves in the Northern Hemisphere. It's just an illustration of the range of events that happen in different locations. So we had heat waves at the same time in North America, in Europe, and also in Asia. And you see here the different impacts that were induced by these heat waves. As mentioned, also Sweden was touched by increase in heat wave impacts also on health. And basically looking at the probability of having such a strong, large area affected by heat waves at the same time, you can find that the probability of such an event has been strongly increased by our influence on the climate system. Now we have seen that already in observation, we see strong changes in mean climate, but also in extremes. But what will happen in the future, in the coming decades? Especially after 2030, because we should say that now in the coming years, because of the emissions we have had, and of course also emissions which are committed by current infrastructure, we expect to reach 1.5 degree in more or less 2030. But what is at stake is whether we manage to stabilize temperature, which will mean that we would need to have no more CO2 emissions by about mid-century and decrease CO2 emissions very quickly in the coming years. In that case, in the best scenario, we could stabilize temperature at about 1.6 degree and maybe even decrease it afterwards. And that's the estimate for mid-century, so 2050 more or less. So you see in the best scenario, we would be at about 1.6 degree. But in the worst scenario, we would have already much higher temperature in mid-century. And now, if we look at possible projections at the end of the century, could really go in all different directions, stabilization, again at about 1.5 degree in best case, but in worst case, possibly temperatures of up to about 4 degrees or more. Here I'm showing the actual scenarios. These are the projections of CO2 emissions, and I think it's important to keep in mind, if we want to, we could emit a lot of CO2. That's basically this trajectory here in dark red. So we really need to change our way of life if we don't want to be on this trajectory. But not only this, it's not sufficient if we just stabilize temperatures, stabilize CO2 emissions, because in this case, temperatures will still be increasing substantially. So actually, the only scenario that is consistent with the stabilization at about 1.5 degrees is light blue scenario. And in this case, and I'll mention the numbers in more detail afterwards, we need to have very strong reduction of emissions right away now in the coming years. So I would say we are at a crossroad. We need to reach decisions right now, which would have very strong implications in the coming decades. Now, what will happen in terms of change in climate is that if we have more global warming, we'll have more changes also on regional scale. This is an illustration of changes in temperature. It's showing what we have so far. So observed change in global warming at 1 degree. And so the simulated and observed change are very similar. But if we are looking at projected change at different levels of global warming, so for instance, 1.5 degree, 2 degree, or 4 degree, we say that with increasing global warming, we would have much more regional warming. Same thing also for change in precipitation or sun moisture change. So we see with increasing global warming, the changes become larger. So what we see is that the level of global warming will reach, which we know depends on how much CO2 we see emitting, will be also directly related to regional changes, including changes in climatic streams. So we find that many changes in the frequency and extreme intensity of climatic extremes become larger with increasing global warming. This includes effects on hot extremes, marine heat waves, heavy precipitation, agriculture and ecological droughts in some regions, and the proportion of intense tropical cyclones. And we have already much higher risk at 2 degrees compared to 1.5 degree, and also at 1.5 degree compared to now. So with every increase of global warming, we have more risk, but this gets even much worse above 2 degrees. So I'm just illustrating this here about the change in frequency and intensity of extremes in the case of hot extremes. And here we are looking at the change in frequency of an event that without human influence would have happened once every 10 years. And here now at about 1 degree, this event is about 3 times more likely. So it's happening about 3 times every 10 years. So we are seeing that already in observed change, we have major modifications compared to the situation where we would have no influence on the climate system. But we see that at 1.5 degrees, such an event would happen 4 times every 10 years, and at 2 degrees would happen 6 times every 10 years. So you see that even this difference between 1.5 degree and 2 is very substantial. So basically, going to 2 degrees, there's no guarantee that we would be in a safe climate, could actually imply that we have twice as many heat waves as we are having now. And we're already having many such extreme events. At 4 degrees, basically every summer would be extreme, but I would say even at 2 degrees, having 6 summers out of 10 being extreme is obviously a very strong change. We have also a strong increase in intensity, and the increase in intensity is larger than the mean global warming. So for instance, when you have 2 degrees of global warming on average on land, the intensity of hot extreme increased by about 2.6 degrees, and that's because we have more warming on land than in the global mean. We find similar results also for instance, heavy precipitation, where we have an increase in frequency of heavy precipitation events, but also an increase in intensity. And in this case, I think here it's a change in intensity that really matters. So for every degree of global warming, we have an increase in intensity of about 7%. So we have in the past already on average an increase of 7%. At 1.5 degrees, we would have an increase of almost 11% of the intensity. And at 2 degrees, at 14%. So it would be twice as intense. Well, the increase would be twice larger compared to what we have had so far. For droughts, we also have increased intensity and frequency, but only in part of the land area. And here I should say it's only for those drying regions, which show a substantial signal at 2 degrees. Nonetheless, I think it's important to realize that other regions could be affected. Obviously, this is relevant to Scandinavia if you don't look only at the annual changes. So here I'm showing another figure from our chapter, which is showing the change in soil moisture drought on one hand in summer, so June to August, and in December to February. And you see in this case that you even get a signal in Scandinavia. So we see that if you look at, for instance, the seasonal time scale, you can also get a signal in other regions beyond those for which we had a very clear signal in droughts. Regarding changes in compound events, with further global warming, every region is projected to increasingly experience multiple change in climate impact drivers, including extremes. I'm showing here some examples. So many regions are projected to experience an increase in the probability of compound events with higher global warming. And this includes in particular concurrent heat waves and droughts, which are likely to become more frequent. So that's a really important change. Also, we would have further increase of fires and compound flooding, as we have already had now, but it would be even more intense. And we would have also more concurrent extremes at multiple locations, which become then more frequent, including in crop producing areas. And this would be stronger at 2 degrees compared to 1.5 degrees. That's another point where you see that avoiding going up to 2 degrees would be really important, because you would have much more impacts at 2 degrees compared to 1.5 degrees. And that's highly relevant for countries importing food from other regions. I wanted also to highlight some other changes which are substantial between 1.5 degrees and 2 degrees. So if you here look at the risk of wildfire damage, we are at about 1 degree in a range of moderate risk in yellow. And we see that in the case of fire, we will go into high risk at above 1.5 degrees. That's an assessment of the IPCC land report. And so, for instance, above 2 degrees, above over 50%, there would be an over 50% increase in area burned in the Mediterranean region. Regarding food supply instabilities, which I think is one of the risks that I would be concerned about, because it implies, regions really which are also non-local. You see that at the moment we had moderate risk at 1 degree, but at 1.5 degree, we would have periodic shocks across regions. And so already being in high risk and above 2 degrees would get into very high risk. So we see for both of those risks, it does matter very much that we limit global warming at 1.5 degrees and don't go up to 2 degrees. Now, last topic I wanted to mention, which is related to droughts, and it's also a work that we have done in our group, is that we have found a global relationship between droughts and the carbon cycle. You see here from observations, the relation between anomalies in water on land and the CO2 growth rate. So that's by how much CO2 is increasing in the atmosphere. And these are based on observations, which are unrelated, totally independent observations. But we see very clearly a strong correlation between the two. So whenever, on average, we have more droughts on land, you see that there is more CO2 increase in the atmosphere. And when we have more water on land, there is less CO2 increase. So suggests a strong correlation between the water cycle and the global carbon cycle. And this is of concerns because if we have more risk of droughts, as we have seen on average on land, this means that we could move more strongly in these directions, which means that you would have more years where you have release of CO2 to the atmosphere through vegetation processes. The other concern is that if you compare those correlations in models and observations, which is done here, so that's a correlation here, and so I don't have here the numbers, but for GRACE, we have about 0.8 correlation. And what we find is that if you look at basically models, which is here the trendy models, this correlation is much weaker. So the model seems to underestimate this correlation. And this may mean that basically they underestimate the potential effect in the future. Now, this is of concern because already we know that with increasing global warming, the land carbon sink becomes less efficient. That's what you see here. At the moment, actually, both the land and the ocean are taking up a lot of the CO2 that we are emitting. That's what we see here. In this scenario, at 1.5 degrees, we would have a very large sink, but the sink becomes less efficient. But what we see is that with increasing droughts, the land carbon sink could become even less efficient, and possibly the models are underestimating this effect. So it might be even worse. From this point of view, I would have some concern about pushing the system too far because we don't know if the models are predicting this correctly. Now I want to finish with scenarios for stabilization. And we have seen that it's really worth limiting global warming to a 1.5 degree. But what can we do? What should we do if we want to limit global warming to 1.5 degree? Here I'm coming back to figures from the special report from IPCC on 1.5 degree global warming. And we are looking at the emission pathways, which are consistent with the stabilization at 1.5 degree. These emission pathways are shown in blue. And there are 7 points that are really important. First, we need basically change which are unprecedented in terms of scale. We have seen before emission kept on increasing. So now not only we need to stop increasing emissions, but we need to decrease them very quickly. So we need to have an immediate reduction of CO2 emissions on global scale, a decrease of about 50% until 2030 compared to 2010. We also need to reach net zero CO2 emission at the latest in 2040, which would give us 66% probability of limiting global warming to 1.5 degree, or 2050, which gives us only 50% chance. And I would say, although we often hear the words net zero in 2050, we should be aware that this only gives us 1 out of 2 chance of limiting global warming to 1.5 degree. We also need some negative emissions. So you see at the end, those trajectories actually have negative emission, which is implying that CO2 would be taken up from the air, either from vegetation, for instance, reforestation or technological methods. But I think we should be very careful about this. And obviously, the scenarios here, P1 or P2, are much safer because these are technologies which have not been deployed at this scale at the moment. We don't know if it makes sense. So I would say at most, it will be of the order of 10% of present-day emission, which is corresponding to those scenarios here. Now I want to finish with the remaining CO2 budget that we realize we are really in a difficult situation. So if you want to limit global warming to 1.5 degrees, these are the remaining CO2 emissions budget that we have. And we have to keep in mind that at the moment, we are emitting every year about 40 gigatons CO2. The remaining budget is for about 50% chance of limiting global warming to 1.5 degree, 500 gigatons CO2. So a little more than 10 times this amount. If you want to have 2/3 chance of limiting global warming to 1.5 degrees, it's 400 gigatons CO2, so it's exactly 10 times more. And in case of 83% chance, you would have only 300 gigatons CO2 left. So if you compute this in terms of remaining years of emissions at the current level of emission, this means about 7 to 12 years. And obviously, this will mean that if we have no change in our everyday life, in about 7 to 12 years, we would be sure that we have basically used up all of this budget. That's why we need to have very strong action right now. But the main point is really having very strong decrease in emissions, but also very quickly. So I mentioned that we need to have a decrease of about half of the emissions until 2030. And this implies basically a decrease of between 5 to 7% of CO2 emissions per year. Clearly, I think the conclusion from this is that we are in a climate crisis and we need to act immediately. Last point I want to mention is what has been assessed after the last COP, which trajectories we are on based on the targets that different countries have put on the table. And currently, based on the 2030 targets of the different countries, we are on the trajectory towards 2.4 degrees. So again, in terms of CO2 emissions, this doesn't mean a further increase of emissions, more of a stabilization. But we are not on track towards the decrease of emissions, which is necessary for limiting global warming to 1.5 degree or even 2 degrees. So the trajectory to 1.5 degree would be here, this gray trajectory. And if we want to limit global warming, we will need to be at about this trajectory here. In both cases, we are above it, so obviously we are not on track. So I come to the conclusions. We are clearly in a climate crisis. We already have more than 1.1 degree of global warming. And if we don't decrease CO2 emissions immediately, 1.5 degrees. Stabilization at 1.5 degree will be out of reach. Extreme events, including heat waves, droughts, and heavy precipitation, become more intense and frequent in many regions, with all regions being affected by some changes. And I think non-local effects are also important, for instance, for food security. So we should not be only worried about changes happening in our regions, but also about changes that are affecting other regions and that indirectly can affect all other regions. We're also starting to see extreme events which are without precedent. I mentioned that. We're starting to see events where you can say you cannot explain these events without our influence on the climate system. So what's next? The first step is we do need to reduce emissions very quickly. And I would say this first aim of halving emission until 2030 is really important. So I think we speak a bit too much of the goals in 2050, which is really far in the future. We need to be aware we need to decrease emissions right now. And we need to have those emissions within really just a few years. That's absolutely essential if we want to be serious about limiting global warming to 1.5 degrees. At the moment, we are definitely not on track. World countries also need to submit more ambitious CO2 mitigation targets at the next COP. And we have facts now. We see climate change is happening. We know what we need to do to limit global warming further or stabilize it at around 1.5 degrees. So we need action, not only words. And I'll finish with this summary from IPCC. Every action matters, every bit of warming matters, every year matters, and every choice matters. Thanks very much for the attention.
Or agricultural drought. Is this actually the case, or we also have unintended consequences in which drought probably is attenuated somewhere, but exacerbated elsewhere?
Yeah, no, thanks for the really good question. So yes, indeed, we have different trends in meteorological droughts, hydrological droughts, and agricultural droughts. So meteorological droughts signals are as weaker because if you look in terms of water balance, the strongest signal is in terms of change in evapotranspiration. So that's affecting both hydrological droughts and agricultural droughts, but not lack of precipitation. So I would say that's important to realize. It's about more than just change in precipitation, and this change in evapotranspiration is really important. Now, in terms of reservoirs, I would say, yes, of course, this can have an influence. Obviously, we need to realize also if you have more demand for moisture, this will also affect the water content in reservoirs. And yes, I mean, we can maybe decrease the risk for hydrological droughts because maybe we can retain some water that can be then used later in the season. So I would say, yes, for hydrological droughts, this can have some impacts. Obviously, for agriculture, if you have irrigation, but this means that you need to install irrigation systems. I don't know the details for instance, in Sweden, but I know in Switzerland, actually, a lot of the agriculture we have is rain-fed agriculture. So even though you could say, yeah, potentially you can adapt, but this means a change in infrastructure, which needs to be taken into account. So yes, I would say we have some ways to adapt, but it could mean substantial changes in the way, for instance, we do agriculture. And finally, there is still the point that in some locations, the water is decreasing so much that even reservoirs cannot counteract this. And if you look at the Mediterranean, for instance, we have a very clear signal there, a very strong drying already in the past, and even stronger in the future.
Thank you very much. Thanks for clarifying that. Yes, there is one more question online.
So this is from Freddy Boucher from Lyon. Dear Sonia, very nice talk. In the recurrent IPCC report, the science discusses increase of temperature extremes, which are actually not so extremes. It describes, for instance, extreme for daily temperature, sometimes at a local scale, sometimes 95 percentile of something like that. However, the extremes that matter more are much more rare than that and have much more impact. How to study better these much rarer events?
Yeah, so I would say no, in the IPCC report, we did look at different types of extremes. So the results I showed with a change in intensity and frequency of hot extremes, I was looking at the 1 in 10-year event, which is indeed not so extreme, but it's already fairly rare event. In the same figure in the summary for policymaker, there is also an analysis for the 1 in 50-year events, which is even much rarer. And there, I would say one important message is that those rarer events, the more extreme events, become even more extreme. So for instance, the multiplication of frequency is stronger for the rarer events. We have a much stronger signal there because these events are basically happening very rarely now, but with a shift in mean temperatures, they become much more frequent. So actually the signal is stronger for more extreme events. So I would say in the IPCC report, we did look into this, and indeed, for very rare events, we have even stronger signal. And as I said, in some cases, we have events which are truly unprecedented, where we see those events would have never happened before. The probability was about 0 without our influence.
Thank you very much, Sonia, also for clarifying this. And indeed, there is always the challenge when one is looking at the extremes to the extremes, where you have very low probabilities to determine that and high uncertainty. But indeed, as Sonia said, uncertainty is there, but this shouldn't prevent us from making decisions. So probably I have a more general question, which was related to what we can do. Since this was the last part of the talk, there will be also a panel discussion later on about more on general aspects related to climate change. But I like in the slide, there was a strong reference to 2030, because indeed I can make many nice announcements of what I want to do by the end of the century, but probably the 2030 would be a closer horizon. But this 2030 also made me think about the Agenda 2030 by the United Nations and the Sustainable Development Goals, where we have 17 different goals, not all of them pointing to the same directions. The goal of economic growth, fighting poverty, fighting hunger, social inequalities. So I was wondering also, in view of your leading role in IPCC, how do we communicate with policy and decision makers? And also, how do you see also our role? In a sense, we have the privilege as white people living in rich countries that have enjoyed probably many aspects of economic growth. How can we play our cards also in telling what other countries should be doing, especially referring to low and medium income countries?
Yeah, thanks for the question. So I think the first point to realize is that in terms of emissions, it's really the highly developed countries which are mostly responsible for emissions. So, basically countries which are much poorer are not having very large amount of emissions. So the question obviously is, no, those countries also want to develop, and we shouldn't say they are not allowed to do this, but I don't think you need fossil fuel to develop. So I think the main point is about disentangling the use of fossil fuels from well-being. You don't need fossil fuels for a good life. Actually, it's exactly the opposite. Fossil fuels is destroying our Earth. So using fossil fuels is not the solution, but we have other sources of energy. We can have renewable energy. We can use solar energy. There are a whole range of options that we have. Of course, in general, consumption is also an issue. We have other pollution that is also induced by this. But in general, in terms of the climate change problem, the main issue is stopping to use fossil fuels. And therefore, this we have alternative. We have renewable energy that is very cheap. And I think this doesn't mean that we have to stop development. Doesn't mean that poor people have to stay poor all their life. It's not what we need. We just need to stop and go away from fossil fuel development, a fossil fuel economy.
Yes, thanks. And indeed, in COP26, there have been references also showing how there is a very small portion of the population which accounts for the vast majority of consumption and CO2 emissions. So probably that is some kind of also message that would help having some concrete change, because my fear, at least, and many scholars' fear, is that if we see, for instance, the trend on CO2 emissions that you have showed, we feel kind of hopeless it seems like, and also there was many times in your slides reference to irreversible changes. So I also wonder about how we communicate this to the public and to the decision makers, because this may also have unintended effect in the sense that if these changes are irreversible, we better focus on adaptation measures rather than mitigation options, which would require many sacrifices. And indeed, there are also lobbies that are pushing in that direction. And we also see that more and more children are suffering, they are anxious, we have serious issues, and I really wonder whether this feeling of hopeless is something that really helps to change our society. Probably some...
I totally agree with that. I don't think we should be hopeless. I mean, it's just to say the situation is very serious. And yes, some changes are irreversible. I think we need to accept that. The problem is there is no way to communicate in a nice way because it is the way it is. But I think maybe the diagnosis is, yes, there are some changes that have already happened, which are irreversible for, many centuries. But these are still limited. And so what is at stake is not, about going back to climate we had 150 years ago. It's about not going much beyond what we have at the moment. And it's just to realize that our decisions now will have very long-term consequences. And it will have long-term consequences for us, for future generations, for children now. And just realizing this, I think, is really important. So my point about highlighting irreversible change is not so much about looking at what has happened so far. It's much more about looking at the future and understanding. I think sometimes there is this perception of, it's also something people comment sometimes like, okay, but if it gets a bit warmer, it's not that bad. We know in some regions it's bad, but so some of the change are okay, but the problem is we know some of this change are extremely serious and we are destabilizing the Earth system. The problem is once we would be, for instance, diagnosing that we have passed some tipping point which can happen, we could not go back. I think that's the main issue we need to be aware. It's not like other issues where I can say, okay, we are doing something wrong, and then if we stop, we go back to the station before. We need to understand the long-term consequences of our actions. So yeah, I think that my point about irreversibility is more about looking forward at what will happen. And I didn't mention this in the talk, but also in the 1.5 degree report, one topic that was discussed a lot was also impacts on biodiversity. And there also we have irreversible impacts. But I would say a lot of those impacts would happen between 1.5 degree and 2 degrees. So I would say limiting global warming to 1.5 degree does avoid a lot of those irreversible impacts, and including extinction. Now about anxiety, it's also a comment I get a lot about, how do you keep, how do you make sure you don't get too depressed by this information? I think we need to realize we have a challenge. We need to be active. We need to make sure that we avoid those worst case scenarios. And I think we can do it. So in the 1.5 degree report, we had some storylines that we wrote across the different chapters where we outlined what those different worlds could look like. And we have one storyline which is consistent with 1.5 degree. And I think the point is this is a nice storyline. So not only we avoid very strong change in climate, we have already some now, but it will be a bit worse than now, but it's within the type of climate we know at the moment. And yes, we just need to change our society so that we stop emitting CO2, and it's doable. Like we just have, to make sure we don't have any more petrol cars pretty soon. We need to move to renewable energy, and it's doable. We can do this in a world that is nice to live in. And I think that's the message I would like to give. It's not that difficult. We just need to move away from fossil fuels.
Now we have two more lecturers. The first one is Dr. Thomas Stevens, who is an associate professor at the Department of Earth Sciences. Tom is a physical geographer and an international leader in the field of dust and climate interactions. And he will give a talk entitled "The Past is the key to the future, climate change over geological time. It is a real honor to have you here, and looking forward to your talk.
Thanks, Giuliano. Thank you very much, Giuliano, and thank you for the invitation to be part of this fantastic symposium. It's a real honor to be joining this. What I'm going to talk about today is climate change over geologic time. What do I mean by geologic time? Well, that can be anything from just before humans have started to actually actively record and observe climate changes. So a few hundred years ago, all the way back to 4.6 billion years ago at the beginning of the Earth. So we have a huge span of time, 4.6 billion years, which I'm going to try and condense into 20 minutes. So that's my challenge for today. But that's going to be impossible, of course, but what I want to try and get across most of all is variability in the climate system from geologic records. How much change there is in the geologic record of climate change. And I think this picture here from the National Geographic on the title slide here sums that up. We're looking at a resident of Baffin Island on the Arctic Circle in Canada, where he lives today in the Arctic tundra with lots of ice, holding up a picture of what his home would have looked like 55 million years ago during an exceptionally warm period of Earth's climate. So more like a subtropical swamp. And this total transformation of the landscape, total transformation of the environment is all down to climate change. But I think it's a good place to start, actually, if we look at what we go to something that we're all here today for a reason. That's the 300 years of weather statistics from Uppsala. This is the temperature record, annual mean temperature record for Uppsala from the beginning to 2020. So just about 300 years of weather statistics. And in terms of observational records, this is one of the longest in the world, and there's only a couple that are longer and only slightly longer. And so it's pretty much as good as it gets in terms of our observations of climate by humans directly and recording them. So 300 years or so. And you can see there's the bars back and forth here are individual annual observations of annual mean temperature. But I want you to focus on this dark bold line here. That's the 30-year running mean of average temperature. And you can see, broadly speaking, that over the course of the record, with the exception of the recent decades where we see very strong signal from anthropogenic warming, most of the variation in that 30-year running mean is within less than half a degree or so. Now, what I'm going to do now is take that Uppsala record, remember our sort of best case for human observations of climate, and I'm going to condense that down and put that in the context of a longer record from the geologic past, in this case a record of temperature from Greenland, taken from ice cores derived from the Greenland ice sheet, where we use isotopes of oxygen and hydrogen to look at temperature variation over the last 50,000 years. So here's the record, and we're going to shrink it and fit it into that last 50,000 year record and see where it all fits in. That blue bar there is what is the extent of the Uppsala record, that best case scenario for humans actually recording the environment. So what you can see straight away is just how vanishingly small our own observational records are in comparison to this long-term record of change. The second thing that jumps out at you perhaps here is this incredible variation that we see in the Greenland temperature records. With 20 degree difference in temperature between the coldest and the warmest states. Now, this isn't Uppsala, this is Greenland. It's not quite the same. I'm comparing two different things. But the general point still stands. We see a lot more variability in these longer records. On the whole, what we're seeing here is generally colder climate during the last glacial of the Ice Age, so during the cold phase of the Ice Age, the last cold phase, and then an abrupt warming into the current warm state climate, the interglacial, the Holocene interglacial, the last 12,000 years of climate. Within the last glacial, we see these extraordinary bumps in the temperature record. these extremely rapid transitions in temperature. Now we can see from the ice core records that these changes in temperature are of the order of 10 or 12 degrees, and they occur within sometimes less than a decade. So imagine that, 10, 12 degrees of temperature change in less than a decade. These are extraordinarily rapid oscillations in climate. We see nothing like that in our observational records that humans have made. So the message here is these long records are essential because they tell us about long-term changes in climate. They tell us about the capacity of the climate system to vary dramatically and over different timescales. So what I'll do today is I will extend this tour through time. Okay, we're going to go backwards in time and look at different stages of climate evolution on Earth, very briefly, and then think a little bit about how we reconstruct these changes, in what way, and finally just talk about what the kind of relevance is of those records. Okay, so what I'll do now is continue the tour through time. As I said, we'll take this Greenland record, 50,000 years of temperature on Greenland, and we'll condense that down again, and we'll focus on the last 5.5 million years, this time from deep sea marine sediment records, which in this case can tell us about the amount of ice on the planet and the global temperature. So, okay, let's shrink it down, and we'll see how it all fits in. So here's our emerging deep sea record, 5.5 million years ago to the present day. Colder temperatures on the bottom, warmer temperatures higher up. And you can see this little upswing in temperature right at the end. That's the Greenland record. All of that short-term variability is lost in now. We can't see it anymore because we've gone on to a longer time scale. But what we can see is that last upswing between cold glacial, warm interglacial conditions is just one of many, many oscillations in climate that have occurred. Many tens to hundreds of oscillations between warm and cold, operating over tens to hundreds of thousands of years. And these oscillations, these glacial phases and interglacial phases, basically represent time, the differences between these states, this state here and this state here, where we have vastly increased ice masses on Earth during the cold stages, ice growth down as far as northern Germany, as far as New York State, tundra landscapes and permafrost expanding dramatically over the mid and high latitudes, and much lower sea level, to something more like today, where we have much reduced ice coverage in the northern hemisphere, and we have much higher sea levels, and we have a total transformation of vegetation and landscape. So these are glacial, interglacial cycles. And what we're seeing here is, during this phase of time, this is what we could think of it as the Ice Age, the current Ice Age, we have these incredible oscillations between these different states, repeatedly, over and over again. Now, you can also see here that there's a general tendency towards lower and lower temperatures, more and more ice, and a general tendency towards increased variability within the climate system, so much larger amplitude swings and oscillations in climate. So we're changing from a world which is relatively warm and stable to a world which is extremely dynamic over these tens and hundreds of thousands of years. But we can extend this record still, so now we're going to take our 5.5 million year record and we'll take another leap backwards and we'll extend that marine record for the last 65 million years, so that's since the end of the dinosaurs, basically. And we'll see how climate has evolved over that time period. So let's reduce that, 5.5 million years, and we can see how that fits in on the 65 million year record to the present day. You can see this was the bit that we were just looking at, this descent into colder and colder conditions, descent into ice house conditions or ice age conditions. But you can also see that when we go further and further back, what we're looking at is, in fact, with that last reconstruction, we're just looking at the tail end of a long, long global cooling occurring over tens of millions of years, transitioning from a climate here about 50, 55 million years ago, where there's no ice on the planet, where sea levels are over 100 meters higher, and we have a sort of supercharged hydrological cycle. transitioning from that gradually down through increased ice volume to colder and colder, more ice-rich climates like we're in today. And indeed, ice starts to appear, first of all, on Antarctica only about 34 million years ago, and then in the northern hemisphere, Greenland, 5 to 10 million years ago. And that's really the story then of this climate change over these tens of billions of years. This is the story of a transition from a greenhouse world, a world dominated by hot, sort of very active hydrological cycle and high sea levels, to an icehouse world. So a total transformation. Incidentally, this is represented here by the slide I first showed, with the transformation of Baffin Island from this kind of swamp, subtropical swamp type environment to a tundra and ice caps. So we'll do this one more time before we stop with this tour through time, and we'll actually condense that 65 million years ago, and now we're going to go really far back. We're going to go back 500 million years, and we're going to look at climate change over such a long time scale. This is almost we're getting closer towards the beginning of a sort of complex animal life. So let's condense that record now, 65 million years, and look at it in the scale of the last 500 million, and see what happens. There you go. There's our descent from greenhouse conditions to icehouse conditions. In the last, actually, it goes back to 100 million years or so, a continuous descent or a discontinuous descent. But what you can see, perhaps, straight away is that this isn't the end of the story. What we've got over these hundreds of millions of years is these grand-scale oscillations between ice ages and greenhouse states. So there was a previous ice age in the Carboniferous and in the Permian 300 million years ago, and you have a previous hothouse or greenhouse state in the Triassic about 240 million years ago. And what you can see over these hundreds of millions of years timescales is that Earth's climate state oscillates between these two different states, greenhouse and icehouse worlds, over hundreds of millions of years, repeatedly. And it's driven by plate tectonics and it's driven by volcanism. Okay, so that was a really quick tour through time. There's actually a lot more we could do because there's 4.5 billion years of this, and we've only gone through 11% of that, but we'd be here all day if I continued like that. So what I want to do, you get the point, I hope, basically, that there's a great deal of variability within the climate system. And not only that, but that variability is operating at a vast number of different scales. So we have hundreds of millions of years oscillations, and we have thousands of years, tens of years oscillations. So variability superimposed on variability. And that's why we really need to look at these long records to understand that. Now, how do we do it? That's the next part of the presentation. And there we need the geologic record. What's the geologic record? Well, we need rocks, sediments like this. We need landforms. We need ice. We need to look at properties of that material laid down in the past that can help us decipher clues about past climate, to help us decipher what has actually happened by looking at the characteristics of these sediments, rocks, and landforms. Now, the problem with the geologic record is that it's not a great record, to be quite honest with you, in many ways. And I think that's typified or summed up quite nicely by this quote by Charles Darwin. So I look at the natural geologic record as a history of the world, imperfectly kept and written in a changing dialect. So a badly kept book written in a changing dialect. Of this history, we possess only the last volume relating to 2 or 3 countries. So it's incomplete area coverage, incomplete time coverage. And of this volume, only here or there a short chapter has been preserved, and of each page, only here or there a few lines. It's a book with most of the pages ripped out and most of the lines rubbed out. Now, okay, things have improved since Darwin's time quite a lot. We have much better records now, and we have much better ways of looking at those geologic records. But I think the general point still stands, and that is that the geologic record is fragmentary, hard to interpret, often very difficult to decipher, and we only have very small pieces of evidence that we can use to piece together this climatic puzzle. So past climate scientists are not often such, these stereotypical scientists working away in extremely highly constrained experiments with very well constrained parameters, very tightly defined. what we're more like often is detectives trying to piece together like a kind of crime, who done it, a climatological crime scene. How can we reconstruct climate or know what's happened in the past based on such fragmentary, isolated bits of evidence? So what is the evidence? Well, I've mentioned a few lines, okay? One is the marine record. Now, in deep marine basins away from continents, sediment builds up over long periods of time in relatively stable conditions, and this is where we can derive our long records of climate, like these tens of millions of year records, by drilling into these sediments and recovering cores of sediments. These sediments are laid down through time, of course, and they contain many things, but one of the things they contain are fossils, microfossils, of small organisms like these foraminifera that live in the ocean. And they build their shells in part from the material around them in the ocean water. And so the chemistry of their shells reflects the chemistry of the ocean water. And that ocean water chemistry is a function partly of climate. So, for example, ice volume on land or temperature in the ocean. So changes in that through time are recorded in those shells that we can then core and measure through time from the sediment records. That gives us nice long records. If we want to go into shorter time scales, we can look at, for example, ice cores, like on Greenland. And ice builds up over time in layers, and when you have quite quick ice accumulation, then we can derive almost annual laminations, annual scale climate reconstructions, even tens of thousands of years ago. And this allows us to look at these extremely rapid oscillations in climate during the last glacial phase and decipher that they happen over tens of years rather than longer time periods. So they give us good insight into rapid climate changes. The great thing about ice cores as well is that when ice forms, it traps atmosphere, pockets of atmosphere in the ice, and you get gas bubbles forming in the ice. And those bubbles are like little time capsules of the atmosphere in the past. So when we core the ice, we can look at not only temperature or other climatic parameters, but we can also reconstruct atmospheric composition by looking at those gas bubbles, greenhouse gas composition, for example. Now, one of the records that I'm most interested in is called LERS here. And this is a picture from northern China of this sediment record. You can see some people down here for scale. What is LERS? Well, it's the geologic record of this, dust storms. So dust, what I mean by that, I mean fine-grained material, finer than sand, blown around in the atmosphere and then deposited over thousands to millions of years. And then as it gets deposited, it builds up these thick sequences of LERS in some parts of the world. If you look closely, you can see these faint, darker bands, maybe, in the LERS. And these are actually ancient soils developed when climate was warmer and wetter and shown in the LERS record, and then you have more dust being deposited on the top from more dust storms. Here you can see these bands more clearly. This is a picture from Tajikistan, from one of my research projects, where we can see some ancient soils here, and another one here, and then some actual sampling of this material. And these are great climate records, the LERS records, because they tell us about climate on land, where people live and where we have actually ecosystems changing that we experience ourselves. And also because they are, because they are, sometimes these records actually contain records of human activity. So human artifacts, stone tools. And indeed, these records in Tajikistan, in Central Asia, have quite a few layers which show different stone tools from waves of human migrants that have come through the area and lived in the area. So we can use the LERS records to look at climate change over that period and look at migration and occupation of humans and how they technologically changed. So this is over the last million years or so. So it's a fantastic way of looking at our evolution in the context of climate. And this is what one of my main projects is at the moment, this FOCA project, the timing and ecology of occupation, human occupation of Central Asia. I'm going to show you a couple of pictures, a few pictures from that, just to show how we sample this stuff and how we work with it. So we raid the local hardware stores and we try and get any kit we can to get the material out. Chainsaws, sanders, knives, hammers, and so on. Tape measures, more hammers and tubes, even sophisticated things like compasses to get this material out of the section. And we end up with cut sections that look a bit like this, where we've taken our samples through the sections by depth. Just keep your mind on this picture here on the right-hand side. You can see a person for scale. Now we're going to look at a drone video taken from the other side of that picture, so we see it from the valley. That is the section that's cut, and this is the drone video. This is in Tajikistan, covering the last 1 million years or so, hundreds of meters of this material. So there's a cut section. There's some people sampling down here for scale, and some more cut sections and steps covering them, between them. We sample this stuff at 2 centimeter resolution, over hundreds of meters like that. And we take samples, sometimes many tens of kilograms in size, to run various techniques and methods to understand climate. It's a huge operation involving tens of people over weeks and sometimes months, and very, very labor-intensive and very hard work, and sometimes very tough conditions. I hope this gives you a sense of the scale of this material. Remember, this is dust storm deposits over millions of years, and these also contain layers of human artifacts. So the scale is quite extraordinary. Okay, but why? Okay, I've kind of said why, but I also want to think more in the future as well. How is this relevant beyond just of interest, I suppose? And that's where I come back to my title, The Past is the Key to the Future, because this is a bit of a play on words on the concept of uniformitarianism, which is a concept we use in earth sciences and underpins earth sciences, and brought in the Enlightenment period by James Hutton and Charles Lyell. And the idea is that the present is the key to the past under this concept. So what we can say is that current processes, natural laws that operate today are exactly the same as those that have operated in the past. Nothing revolutionary now, of course, but very revolutionary back then. So what that means is that we can use our understanding of the present and present processes to interpret the geologic record. But I think with past climate science, we can actually reverse that, and we can say our understanding of the past climate allows us to understand the current climate system and project better into the future. And that's what I want to talk about now. So we can reconstruct many aspects of climate here. Ice, amounts of ice, dust in the atmosphere, permafrost, aerosols, and as I pointed out before, carbon dioxide or greenhouse gases in the atmosphere. Let's focus on that latter one because it's an obvious, important case. And just to finish up, what I'm going to show you here is a record from Antarctica, ice core record from Antarctica, covering the last 800,000 years that shows CO2 reconstructed from the ice versus temperature reconstructed from isotopic composition of the ice over the 800,000 year period. And you can see how extraordinarily tightly coupled temperature and CO2 are over this time period, over hundreds of thousands of years. These oscillations are glacial interglacial cycles, those changes between very warm and cold states within the ice age. And over those timescales, CO2 is very tightly coupled to the temperature, to climate. Now, we can go back further with our CO2 records, but we run out of ice after a while. So we have to use other ways. And then we can use marine sediments again, and indeed looking at isotopes in marine sediments of foraminifera or biochemical markers, and reconstruct CO2 that way. And here is the same record I showed previously, 70 million years to the present day, and then we've got the global cooling from a greenhouse world into an icehouse world here. And then our CO2 changes are recorded in blue here, reconstructed. Now there's more uncertainty on these records, but you can still see the extraordinarily close match between temperature and CO2 over tens of billions of years as well. And this is a relatively new record that's come out just late last year, showing an extremely close connection over these timescales. How does that relate to the future? This is the same CO2 record for the last 70 million years here, over tens of millions of years, and then expanded a bit here, hundreds of thousands of years. and then projections into the future in terms of atmospheric composition of the amount of CO2, concentration, based on these SSPs, these shared socio-economic pathways that the IPCC uses to model how future atmosphere might look. And this is based on socio-economic changes, geopolitical changes, technological developments, and so on. So there's a big range of possibilities here. One extreme case up here, and then we have a number of more realistic, I hope, and more optimistic, maybe, cases down at the bottom. And you can see where these correspond to in terms of amount of carbon in the atmosphere. So just to say these more realistic ones, these lower estimates here, take us to levels of CO2 in the atmosphere that exceed anything that our genus has seen since it's evolved 2 million years ago. And they take us to a time when, well, the last time we saw levels of CO2 like that, we had beech trees growing in Antarctica. The more extreme versions take us, though, to an equivalent time where CO2 was at levels where we were in that completely different climate state, in that greenhouse state, where we have alligators swimming around in the Arctic, sea level 100 meters higher than today, and no ice on the planet. So that gives you, I think, a nice context of these potential future changes in climate based on what we understand from past records. So the key message here, I've gone through a huge subject in a very short space of time, but what I want to get across here is the incredible variability that we see in the climate system over hundreds of millions of years, tens and so on, all the way to thousands of years. Variability superimposed on variability, sometimes extremely rapid and very changeable, and that has profound consequences for our environment, which I think is what the famous paleoclimate scientist Wally Broecker meant when he came up with this quote that climate is an angry beast and we're poking it with sticks. It's an angry beast because it has enormous capacity for wild swings and unpredictable behavior, big changes that come and go. And of course we're poking it with sticks because of our landscape changes and our emission of greenhouse gases. And of course, we know that. We know how angry this beast is because of past climate records, because we can look in the past and go beyond our observational records. Thank you very much for your attention.
Thank you very much, Tom. I'm going to check if there are some quick questions, otherwise we will take them for the panel discussion. Yeah. Okay, we will take it later. So thanks again, Tom, for this wonderful journey across different timescales. It has been really fascinating, and we will discuss this more in the panel discussion. So I will now introduce the last but not least speaker for the morning, Professor Ghia Destuni, who is a professor of hydrology and water resources at Stockholm University. It's a true honor to have Professor Ghia Destuni here. She has been a global leader in the field of hydrology and water resources. She had many roles also in Sweden. For instance, she was the Secretary General of the Swedish Research Council, Formas. Many of us have applied to that, I guess. And also she received many international honors, prizes, and awards, including the Darcy Medal by the European Geoscience Union, and she is also a fellow of the American Geophysical Union. So it's a true honor to have you here, Ghia. The floor is yours.
Thank you. I'm trying to get this to work. Thank you so much. Well, thank you again for inviting me to talk here today. Does this work properly? I don't know. Yeah, good. So what I will talk about is climate and water, water and climate, and with the focus on water on land, which is symbolized here by this schematic drawing of a catchment, hydrological catchment. But that doesn't mean that we are just going to look at water in the landscape, essentially the freshwater system, in bits and pieces here and there, locally, in details. We are going to look at catchments, but we are going to look at them all over the world. And the aim is to understand how the messy details and noise that you have in the landscape when it comes to water, does that lead to overarching global patterns so that we can look also at the freshwater system on land as a coherent whole system and see how it interplays with climate and climate change? So to do this, we will also go a bit back in time, look at the past to try to understand what can await in the nearest future, because we're only going to go in the nearest past when we have direct observational records of what it is we want to look at. And to put together all these different types of data, this is ongoing synthesis and the meta-analysis work of data that from a series of works over several years with many different people that we are now combining to try to get this large-scale picture of the freshwater system. So, the blue marble, right? It's a water world, it's, you know, a planet. But in fact, the water on our planet is not so much. So if you put it all together to scale as a drop over the whole globe, you get that big drop, which is not as big, and that contains all water on Earth, including the oceans that are most part of that. When you go to the system I'm going to look at now, the freshwater system, you go to a very, very small middle drop that's all liquid freshwater, of which most is under the surface. And the water that we see and commonly think about when we talk about the freshwater system, the water in lakes and rivers, that's a drop so small you cannot even see it nearly on this picture. So a tiny system like this, why do we want to look at it? I mean, what does it matter? Is it just details? Well, the thing is we live on land and we are very dependent on the water on land. And that's also how we, to a large degree, experience climate change, through trends and shifts of the water conditions on land. For example, if we have less or more freshwater availability, that has great importance for our societies and ourselves and our ecosystems. And also if we have more frequent, more intense droughts or floods, which can be also of longer duration, that also plays an enormous role for our societies, our safety, our well-being. So that's why we need to look at this system and understand how it interplays with climate. And there are lots of questions one can ask about this interplay, but I'm going to focus on just a couple of them today in what I will highlight here. So we want to understand, among many other things, or in general, how climate change combines with human-driven landscape development. So things we do in the landscape itself, ourselves, irrigate, for instance, and build dams and whatever we do. How does this interplay work to change water conditions on land? And one important question that is asked is, does this combination work towards accelerating or decelerating landscape water fluxes? So this is a messy picture, a noisy picture, but let's see if we can get a glimpse of what that looks like. So we will focus on those small drops here, forget the oceans for a while, and we are going to look at catchments. I tend to say the because tiny as it is, this water is fragmented in the landscape as different landscape features, lakes, streams, groundwater, wetlands, snow, ice. So we need to understand this distribution, but we are going to use the catchment lens to go through the globe, but we are not going to look at the details of each catchment. So, this is one way of looking at this combination or understanding what do important landscape developments by humans directly in the landscape and what does climate change overarching, how do they combine to change water conditions. So we will look in this presentation have two sets of catchments over the world. So the right map here shows a set of catchments that are very well investigated, where we know that human, because they have been investigated with lots of different data, so we know that they have been disturbed by human developments. And then on the left map, we have a sample of catchments all over the world that are selected not because we know what happened there, but because we have the records of direct records of hydrological variables, so we can look at what they look like in comparison to the other ones and see if there are any shifts between these that go beyond changes that we see from climate change that are common, should be common for both. Okay, so what do I mean by this catchment lens that we take through the world? Well, the good thing about the catchment is that it's topographically delineated, constrained, so that more or less most of the water flows out through an outlet, and that's where we have measurements, direct observational measures of runoff. And then we can also, for the same area, have the precipitation that goes in to the catchment and the evapotranspiration, that is another flow out from the catchment back to the atmosphere. If we also have records of storage changes within the catchment, then we can, for any catchment unit of any scale, close the water balance in purely based on observational records, except for evapotranspiration, which is not usually measured over such scales, but because we have the water balance closure, we can derive evapotranspiration also from actual measurements of all the other variables. So that's why it's so good to, instead of cutting the landscape in just even grid cells, to cut it in catchment-wise, because then we have very good chance of constraining what these fluxes look like, because we have to close the water balance. It is closed. So this is not a question, so now I've taken away the details, so this is not details of going into every lake and stream and what happens here and there within each catchment, but it's a question of looking catchment-wise, closing the water balances catchment-wise, going around the world, looking at the time series of these different fluxes and see how they interrelate. And so we have two of them. Well, one direct water flux, the precipitation that is determined by atmospheric conditions, and that determines how much water goes into each catchment. Then we have the evapotranspiration, that is a land atmospheric change. So it is a matter both of what happens in the landscape and what that looks like, and what happens in the atmosphere. And we have the runoff and storage changes that are purely landscape conditions. So as landscape fluxes, I will look here at evapotranspiration and runoff, because they they are dependent also on what happens in the landscape. And then we have precipitation that goes in, that's an atmospheric. And then we have the temperature conditions in the atmosphere that is denoted here by this aridity index, which is a potential evapotranspiration normalized by precipitation. And that tells us what limits the magnitude of actual evapotranspiration. So if we have potential evapotranspiration above, relative to precipitation above 1, we have water limitation conditions. If it is below 1, we have energy limitation conditions. And that's what you see now if we go into these different catchment sets. That's what you see with different colors here. The blue-colored catchments in this catchment sample are water limited. The red ones are energy limited. That relates to this aridity index. And then you see they have numbers that have different colors. And that relates to what kind of disturbance we know have been major within this observational record that we have for each catchment. So we have blue ones there. We have flow regulation that has expanded widely over the study period. We have green ones where we have rain-fed agriculture that has expanded greatly or been intensified. And we have the pink ones where we have irrigated agriculture that has expanded greatly. And we know this because these have been studied, catchment by catchment very closely, and we have land use and water use records in addition to the hydrological records over time. So then we have the other sample, the world sample, where we don't know what's disturbed, what's not disturbed. So we use this as a representation of what things look like over the world. And here we have 52 non-overlapping large catchments. Each one of them is at least 100,000 square kilometers large. And we chose those to also understand, to not have overlapping catchments, but to understand spatially what happens around the world. And together, they represent very different climatic conditions and climate change conditions and variable human-driven landscape developments. And these have records from at least 25 years from the first half and 25 years in the second half of the last century. So that allows us to get long-term average conditions over at least 50, for some of them 200 years, of what things look like spatially. And it allows us to divide the study, the observational record, in two halves that are still long enough so we can compare how average conditions have changed from the first to the second half. The same goes with the other set of catchments. They are smaller. They're, well, mostly smaller, but they're also very large ones. So those have a very variable size. They are also non-overlapping, and most of them also have records from the first to the second half of the last century. Some, at least one of them, has only a record in the last decades, 3 to 4 decades, but we know that major developments have happened there also in that time, so that's why we include also that. Okay, so let's look just how some results look like. So on the left, you see how the potential evapotranspiration in these different catchments is distributed over latitude. And you will see always here the gray triangle symbols are for the world catchment, and the color symbols, bigger ones, are for the disturbed catchments. So we see when it comes to potential evapotranspiration, basically climate, and you see statistically on the right-hand side how precipitation looks like in relation to potential evapotranspiration in these catchments. You see that the world sample and the disturbed sample look very similar. right? That you can't distinguish it, which means that the disturbed sample also samples most of the conditions you see in the world sample. So now we are looking at long-term average atmospheric conditions, and they exhibit similar statistical and latitudinal patterns. Now, if we look at the landscape long-term average conditions, you see somewhat of a shift between the world sample and the disturbed sample. And we see here, I forgot to say, average evapotranspiration on the left side in relation to average precipitation. You see there is great dependence of actual evapotranspiration on precipitation and not just on potential evapotranspiration. You see on the right side, the latitudinal distribution. So when it comes to long-term average conditions, the shift is really because the sample of disturbed catchments is from high latitude, relatively high latitude areas, the northern hemisphere, and that gives it doesn't have the same coverage as the world sample. So it's similar pattern latitudinally, but some statistical difference of narrower longitudinal coverage of disturbed catchments. So when it comes to long-term average conditions, things look very smooth and similar. But now we are looking at change. That's when things starts to be different. Now we are looking, how have these variables changed from the first to the second half of the study period? And here we start to see the shift. So again, we are looking at evapotranspiration change in relation to precipitation change statistically on the left-hand side, latitudinally on the right-hand side, and you see clearly shift between how changes have occurred, what changes have occurred in the disturbed catchments relative to the world sample. So overall, whether we looked statistically over the world or if we look at the latitude where these catchments come from, we see a clear increase in much higher increase in evapotranspiration in the disturbed catchments, and in fact similar, more or less, whether they have been disturbed by irrigation, dams, or whatever. There has been an increase in evapotranspiration relative to the world sample. So you can look at the point of zero precipitation change. In the world sample, that is not overall disturbed in the same ways as those known catchments. If you have zero precipitation change, you have on average also zero evapotranspiration change, but not in the disturbed catchments. You can have zero precipitation change and quite high evapotranspiration change. And I should say, I only show here evapotranspiration. Things look very similar for runoff, but in the other direction. If you increase evapotranspiration, you decrease runoff because more water goes through the vegetation and evaporation into the atmosphere, and there is less left for the landscape. So here we see shifted patterns, statistical and latitudinal. And we can also identify some catchments from the world sample that behave like the disturbed catchments. Now it's similar results, but now looking at the normalized evapotranspiration, normalized with precipitation. That measure tells us, regardless of how precipitation has changed, has the pattern of partitioning of whatever precipitation water comes in, its partitioning between evapotranspiration and runoff, is that shifted? And yes, in fact, that shifted even more than actual evapotranspiration, because for actual evapotranspiration, you have, or precipitation, you have catchments that have received less precipitation, catchments that have received more, and that also affect the absolute evapotranspiration. But the pattern of partitioning is very much shifted in the disturbed catchment. And we can identify even more catchments in the world sample that we didn't know. I mean, what category they belong to that behave similarly to the known disturbed catchments. And here you can see the world map with some catchment names that are clearly identified as behaving in disturbed ways. So you have Mekong, Krishna, Mudarya in Asia. You have the Barwon River in Australia, Negro and Colorado and Colombia, and all these we know have had major developments of land use and water use. So the method seems to bring out what one would expect for identification of disturbed catchments. So just to put this in a magnitude perspective, the total area of shifted catchments in these samples constitute 16% of the total study area of all catchments. And I should also say that the total catchment area of all catchments covers 25% of the world land area. So this is not a small sample. And we see increase, if we look at what the increase in evapotranspiration has been on average, above any precipitation increase that could compensate some of this. In the shifted catchments compared with other catchments, we see an increase that seems to be directly human-driven of around 37 millimeters per year in these catchments. That if we apply this to 60% of the world land area, then we get a net water loss that has not got back to these catchments in terms of increased precipitation of the order of a flow rate of 26,000 cubic meters per second, and that corresponds to the flow in the world's 8th largest river, Rio de la Plata. So these are not insignificant shift amounts we are talking about. And then to finish with this acceleration-deceleration question, we can look at the changes. So this is change in relative evapotranspiration on the x-axis and change in relative runoff, everything relative to precipitation on the y-axis. And we have these quadrants that we can, and we look where do the catchments fall in this. So we have runoff acceleration, relative runoff acceleration on the top, relative runoff deceleration in the bottom, and relative evapotranspiration acceleration to the right and deceleration to the left. So we can't have both relative runoff deceleration and evapotranspiration deceleration at the same time, because that means water would be lost to somewhere, and it has nowhere to be lost. And the same goes, we can't have relative acceleration in both. So the world sample, we have 50% that have experienced relative runoff acceleration, and 50% that have experienced relative evapotranspiration acceleration. But when we looked at the pattern for the shifted catchments, it's 100% of them have experienced relative evapotranspiration acceleration and runoff deceleration. And if we look at absolute evapotranspiration and runoff acceleration and deceleration, you can see here, if we look at the world sample, that we have a distribution of every type of acceleration and deceleration combination that we can look at, including looking here at precipitation, deceleration and acceleration in combination with the others. But when we come to the shifted catchments, we only have absolute evapotranspiration everywhere, and only in a few catchments we have regardless of whether we have acceleration or deceleration of precipitation. So it's not precipitation that's driving this. And I haven't shown results for potential evapotranspiration, but that's much less, which relates to temperature. So it's not warming that has made these patterns. It's things that we do to shift conditions in the landscape itself. And they are clearly shifted patterns. So, to conclude and summarize, across all study catchments, there is nowhere, nearly nowhere, a simple binary either acceleration or deceleration of the terrestrial hydrological cycle. It's nearly, in most catchments, a mixture of both. So you can have acceleration of evapotranspiration, but deceleration of runoff at the same time in the same place. And whether you have precipitation, acceleration, or deceleration. And across the mixed study catchments around the world, we see indeed a distribution of all types of acceleration, deceleration combinations. And in nearly all disturbed study catchments, we see only green flux, green water flux acceleration, and blue water flux, so runoff deceleration, regardless of how precipitation, if that has been accelerated or decelerated. So just a final remark here is that I haven't showed you results for this, but we have checked it against results from climate and Earth system models, and they really have difficulties in representing these patterns of what happens in the landscape. They don't capture this hydrological complexity and regime drifts that are driven by human local landscape activities. So in addition to the effects of the overarching climate change. So I'll finish here. And thank you for your attention.
Thank you very much, Gia, for the very nice talk. So now I will invite both Gia and Tom to sit here so that we can have a brief panel discussion. This will consist only of, we originally thought of having a...
Yes,
yeah.
but I thought we were going...
Keep the microphone, yeah. So we will go 5 minutes. We will extend the schedule by 5 minutes, so we'll be done by 11:35. But I think they were very nice talks, and it was nice to look at the different dimensions of climate change. Yes, that would be great. And also if I can see Sonia, no, probably I cannot see her here, but I see her. Wonderful. Hi, Sonia. So probably a very first question that I would like to ask, since this was also the conclusion of your presentation, Gia, is related, but also it links to Tom's idea of how a better understanding of our landscape is not only useful to unravel how different type of interactions have resulted into the changes and past trends, but also can help us project into the future. So probably I would like to ask all the three of you how this type of work on the landscape, our understanding of landscape fluxes or interactions, dust and other processes can in practice be used so that global climate models can become more robust and reliable.
Well, I can say I don't think it's a matter of increasing resolution, first of all. It's a matter of understanding what goes on first. So that's what we try to do by looking in the past. Then when we understand that we have these shifted patterns, and we're not talking about just local details, we see the patterns all over the world that we can see now. One way we are using it is to compare directly with outputs from climate models and see what we get. And of course, there is spreading around. And one thing we see is that the climate models generally do a much better job of representing the the temperature conditions and temperature changes and potential evapotranspiration, and that has to do with temperature. They get worse when it comes to precipitation, and then quite bad when it comes to landscape fluxes, because they have not tried to represent them. So now, by looking at what things look like and have looked like in the past, we can start to understand, I think, what types of changes, parameterizations, or what have you, we can enter in climate models and Earth system models to try to represent a bit more of what we actually see from the observational record. This is long-term work. It has taken us several years to put together all this data directly from observational records, and we hope to interact more now with actual climate modeling to see how this can be represented.
Yes. Thanks. And indeed, I think also related to what we discussed before about, for instance, how meteorological drought, trends in meteorological drought may differ from trends in hydrological drought. I think that the role of landscape is,
yes.
I mean, it's also what was shown, and
exactly.
This is kind of consistent across multiple catchments, so probably something that could be included. Tom?
Yeah, it's an important topic and a difficult one because it's so complex. As soon as you start dealing with the landscape, so many different interactions and feedbacks come in. I fell into the trap in my presentation of just showing global climate changes, but of course it's so much more complicated than this, and I think that's where these LERS records that I was talking about are quite important, because from them we can understand the flux of dust in the atmosphere that gets then deposited as these LERS deposits through time. So by reconstructing the rate of accumulation of this dust, we actually can then link that to climate modeling, which tries to understand the amount of dust in the atmosphere and where it's coming from. And dust is a critical component of climate change, mineral dust, in a number of ways. It affects incoming solar radiation, it changes productivity, so the carbon in the atmosphere. Yet it's a product of the landscape, because dust is emitted from land surfaces, soil erosion of rocks. So what we try and do with our LERS records is understand how much of that material has been transported in the atmosphere in the past, which gives us some idea of the potential climate forcing effects, which can then be linked to modeling. Or also trying to trace where that material comes from, the source of the dust. So there's actual origins in the landscape, and therefore what's driving dust emission in the landscape. And all of those things then can be linked to climate models, ground truthing models, increasing our understanding of how much material dust fluxes there have been in the past, and linking that to climate and trying to gauge the potential climate impact and refine and ground truth and test climate models themselves. So that's one of our main aims with that. That's just one example. There are lots of potential examples of this, of course.
Yeah. Thank you. That's really, indeed, I think it's a very relevant example, and I would like to hear from Sonia, who is more involved in the development also of global climate models, your reflections on the role of the landscape.
Yeah, no, I think that's obviously an area also, as Gia said, it's where models could become better. I think, for instance, we have done studies looking at the potential role of irrigation on global scale, and typically climate simulations don't include irrigation. There are very few models that include this, and if we had this, we would actually find that in the models there would be less warming, so of hot extreme. But on the other hand, we could have more in the future once water becomes limiting for irrigation. So I think, yes, it is important, and we could represent it better in models. I would say it doesn't change the more regional and global picture, but of course on small scale it can matter a lot.
Indeed, thank you. And since we are out of the time, and this day is actually a very long one, I have to conclude this discussion, unfortunately already now. And I think there is a lot actually to discuss. We can continue over lunch, because the topic of climate change is is crucial. As Sonia's presentation has pointed out, also we are in a key moment in which key decisions should be taken to address the global climate crisis in the context of Sustainable Development Goals and many other planetary boundaries that we are facing.